In this segment, I want to focus on a law, another dead guy law, called Hess's law. Now, this applies to not only enthalpy, but really any state function, because remember, a state function, a delta, depends only on final minus initial. The pathway doesn't matter. So what Hess's law does is provide us with an alternative pathway to use maybe data that we can gain easier than a goal reaction that we're after. So we've got a goal reaction. It might be really challenging to measure its free energy or its enthalpy, and we can use Hess's law of known values to get at that. Now, this is very similar to what you may have seen in terms of using equilibrium constants. So I want to link those two together. If you haven't had equilibrium constants, then what we're going to be doing is giving you a little preview of what happens when we manipulate reactions. So the first is if you multiply a reaction by a factor. So you can multiply it by a half, you can multiply it by 2, whichever factor is convenient for solving the problem, frankly. Then what you do to the enthalpy for that particular reaction is you multiply it by that same factor. Had it been an equilibrium constant, what we do is we raise k to that power. So you raise the old k to the power of whatever factor you're multiplying by. Okay, so for example, if I multiply by 2, then my new k would be my old k squared. Okay, now if you reverse a reaction, make what is products become reactants, and you have to do that by literally rewriting the reaction. So the products are now represented as the reactants. If you reverse a reaction, then what you do with enthalpy is you change the sign. In other words, if a reaction was endothermic in the forward direction, if you flip the reaction around, it should be exothermic. And that's what changing the sign does. Now, if you reverse a reaction for equilibrium, we take the inverse of our equilibrium constant. Now, if you add reaction, and that's really the heart of Hess's law, that says if a reaction is the sum of 2 or more other reactions, then the enthalpy for the overall process is also the sum. So you simply add the enthalpy values. Now, had this been K, if we had added reactions, we would have multiplied our equilibrium constant values. So those are the rules. Let's take a look at implementing those rules. So in this reaction, we have 3 values here, 3 reactions here. They actually happen to be formation reactions, but you don't have to use formation reactions for this. Okay. Now, this gives us what our goal reaction is. We have 1 mole of ethane, and we want to combust ethane. So we've got 3 reactions we can manipulate to get our goal reaction, which is the combustion of ethane. Ethane is a gas. To combust means we must add that oxygen. You always assume complete combustion to CO2 and water. And I'm going to use water liquid. Sometimes you'll see gas there, sometimes you'll see liquid. And I need to balance this. And you notice it says I want to combust 1 mole of ethane. So in effect, what I'm doing is I am forcing that coefficient to be a 1. And when I then balance, what I find is that I have 7 halves oxygen. And that's not unusual with a diatomic. It's not physically meaningful. You can't have half of a double bond, but it does work in terms of approaching reactions and understanding their energetics and so forth. So that's our goal reaction. When I do a Hess's law, and this is the same thing I've done when I'm adding elementary steps of a mechanism, or when I'm doing for K, I just go left to right, and I ask my question. I need ethane as a reactant. Is ethane only showing up in one reaction? Had it shown up in more than one reaction, I would bypass it. In this case, this is the only place it shows up in our choices, but it shows up as a product. So I have to reverse that reaction. And if I reverse that reaction, then according to my rules above, if it was exothermic in one direction, it must be endothermic in the other direction. It's an 8, sorry about that. Okay, so I've taken care of that. Now I need oxygen. Unfortunately, oxygen shows up in 2 places, and so then you don't really know which reaction to manipulate. And so I'm simply going to bypass the oxygen, and I promise it will all fall into shape. So now I'm going to go to CO2. This is the only place CO2 shows up. I need it as a product. I have it as a product, but I need 2 of them. So I'm going to multiply this second reaction by 2. And that will give me the 2 CO2s that I need. Now, you have to multiply the whole thing. It's something like an algebra equation. If I want to maintain an equality, I have to do to both sides of the reaction the same thing. Now, the rules above said that if I multiplied by 2, then I have to if I multiply a reaction by 2, I have to multiply its enthalpy by 2. Hopefully that's logical. If I form 1 mole of CO2, I release that much energy, but if I form 2, I should release double the energy. Okay, and so then my next one, I need 3 waters. Water only shows up here. I need it as a product. It shows up as a product. I need 3. I only have 1. So do you see the process? You find where it shows up in only one place. Then you ask yourself, is it a product or reactant in terms of what I need? And then it's how many. Okay, so I need to multiply this next one by 3. 3 hydrogens plus 3 halves oxygen yields 3 H2O. And if I multiply the reaction by 3, I have to then multiply my enthalpy by 3. So that's the main process. Now let's take a look and make sure we ended up with our goal reaction intact. So I have 2 carbons, 2 carbons. Those cancel because they're listed as product and reactant. Okay, 3 hydrogens cancels 3 hydrogens. 2 is the same as 4 halves. So 4 halves and 3 halves, there's my oxygen. I still have my ethane, my CO2, and my water. So if I added these reactions, I do get to that goal reaction. Hess's law says that if I add reactions, I take the sum of their enthalpy values. And if I've done my math right, my algebra right, I get 1.56 times 10 to the third, and that would be kilojoules per mole of reaction. I have another video on this concept of mole of reaction. You might want to check that one out. All right, let's do one more quick demonstration of this just to make sure you have this. This one is with free energy. I'm given my goal reaction up there. Okay, so ask your questions. I just go left to right. I need 1 CH4, and it only shows up here. I need it as a reactant. Here it's a product, so I'm going to reverse this reaction. If I reverse a reaction, I'm going to change the sign of free energy just like we did for enthalpy. I need 2 oxygen. Oxygen shows up in 2 places, so I'm going to bypass it and go right for the CO2. I need CO2. It only shows up here. I need it as a product. I have it as a product. I need one. I have one. So I'm not going to change this reaction. And I really should be bringing my states down because you can't cancel a liquid with a gas. So I'll try to be a little bit more careful with that. Okay, gas and solid and gas. There we go. Okay, so we didn't do anything to that one, so we're just going to bring that one right back over. I need water as a product. Water only shows up here. I need it as a product. It is a product. I need to. I have to. So again, I'm not going to do anything to this reaction. Just going to write it over here so you can see that everything cancels properly. Minus 474. Now I'm going to add these up, and if I've done my analysis correct, I should get my goal reaction that was given up above. So 2 hydrogens cancel, the carbons cancel, and I get CH4 gas plus 2 O2, 1 there and 1 there, yields 2 waters, liquid, and 1 CO2. And since if I add reactions, I add their enthalpy values. So what we're going to be doing is we just take a sum of the enthalpy values. And when you add up those enthalpy values, we indeed get the answer that's written there for us, kilojoules for every mole of reaction. So what that means is that every time this reaction proceeds to products 6.02 times 10 to the 23rd times, that's 1 mole that the reaction proceeded, I would release that many kilojoules. Wow, this was a little bit long, but thanks for joining me. It will be worth your patience. This is your best chemistry teacher signing off.